about the Career Academy. Today in this video, I am going to explain the binding energy. In my previous video, I explained regarding the nucleus, its structure, properties. So in this video, an important concept what I am going to explain, that is binding energy. Binding energy. We have studied about the binding energy of a hydrogen atom. I am telling about the hydrogen atom, not the nucleus. The constituents of a hydrogen atom are one electron, one proton. So, suppose the constituent of the hydrogen means one proton and neutron, they are far away. You think that they are at infinity distance. We want to bring them to one place to make the hydrogen atom. So during that time, they release 13.6 electron volt of energy. This energy is called the binding energy of the hydrogen atom. Once again, I am repeating. Suppose one proton, one electron, they are at infinity away, they are far away from each other. We want to bring them close. We want to make a nucleus. During that time, they release some amount of energy which is equal to 13.6 electron volt. So I can say that 13.6 electron volt is the binding energy of a hydrogen atom in its ground state. So I can say that the amount of energy released to bring the constituent of a hydrogen atom, that means one proton and one electron, from far apart to form a nucleus is 13.6 electron volt, which is called binding energy of a hydrogen atom. I am telling about the hydrogen atom in its ground state. Listen carefully. Similarly, I can say that the amount of energy required to break a hydrogen atom into its constituents, means electron and proton, is 13.6 electron volt, which is also called the binding energy of the hydrogen atom in its ground state. Similarly, we will go towards the nucleus. See here, nucleus constitute neutrons. Listen carefully. So, in a nucleus, we know that nucleons are there. That means we find protons and neutrons. So, the amount of energy required to break a nucleus into its constituents means nucleus is called the binding energy of a nucleus. Listen carefully. The amount of energy required to break a nucleus into nucleons. Break into its constituents better, into its constituents means neutrons and protons. So the amount of energy required to break a nucleus into its constituents means neutrons and protons is called binding energy. Otherwise, I can say that suppose protons and neutrons or the nucleons are far away, you can say they are at infinity distance. We want to bring them close to form a nucleus. How much? When they combine together, they release certain amount of energy. That is also called binding energy. I can say that otherwise I can say that the amount of energy released when nucleons means proton and neutron are brought from infinity to form a nucleus is called its binding energy. Now listen carefully. Whenever the protons and neutrons brought together, they lose some energy to make the nucleus. At the same time, we need some energy to break a nucleus into its constituents, means protons and neutrons. Both are equal. Here, I can say that the rest mass energy of a nucleus is less than the rest mass energy of its free nucleons. That means I can write, then it will be better for you. Say that the rest mass energy of a nucleus is smaller the rest mass energy of a nucleus is smaller than rest mass energy of its nucleus when they are in free. That means the amount of energy present in a nucleus is less than the amount of energy present in its nucleus when they are away or they are far apart, you can say. So that difference in energy, that is the binding energy that helps the nucleons to be together inside the nucleus. So for example, you see that suppose I have written the term rest mass energy. According to Einstein, the mass is the condensed form of the energy. That means rest mass energy means the energy associated with the particle when it is at rest. The energy associated with the particle when it is at rest. That means it has a mass, means you think that mass is the conversion of a energy. That energy only stored in the condensed form. So the energy associated with the particle at rest, that is the rest mass energy, whether it is the rest mass of a energy of a nucleus or nucleus. Now for example, rest mass energy of a proton. Rest mass energy of a proton. I am writing like this. Rest mass energy of a neutron. Writing like this. Rest mass energy of a nucleus. Suppose this is the M. Then I can write, so rest mass energy of a proton. So I can write like this. Because mass is written MP, Mn, M. But if I write the energy, I have to use the formula mc square according to theory of relativity, or mass energy conversion equal to mc square. So rest mass energy of a proton I have written. This is the neutron. This is the nucleus. Then the binding energy, if I write it V, I can write this is equal to, for example, protons are Z numbers are present. So I can write this is Z MP plus Mn minus M, taking C square as the common. If Z numbers of protons are there, I can write like this form. This is the binding energy. This one also, in place of a nuclear mass, we can use the atomic mass. In place of nuclear mass, we can use atomic mass. If I use the atomic mass, how it will be? This B will be equal to, now in place of mass of proton, I shall use this term hydrogen atom. This is the mass of neutron, and here I can use, this is the Z, this is the Z plus N. Okay? So it is better I shall write like this. C square. Listen carefully. In place of a nuclear mass, we can use the atomic mass. Here I have written this is the proton, or you can say this is the hydrogen atom. Okay, I have written it is the hydrogen atom, and symbolic form of element Z, Z plus N. It represents the atom with Z proton and N neutron. This one represents the atom with Z proton and N neutron. This represents the hydrogen atom. I said that in place of a nuclear mass, we can use the atomic mass. Okay. There is a little difference in binding energy. You see that here electrons are cancelled. What electrons are cancelled? It contains Z number of electrons. Here also it contains Z number of electrons. So mass of electrons are cancelled. Here masses of electrons are cancelled. If I don't cancel the electron, that means in that atom electrons are there. So definitely binding energy will be little more, no doubt at all. But the small difference in binding energy here neglected. The small difference in binding energy is neglected. Okay, but this is not applicable in case of a beta decay. But in case of beta decay, the cancellation is not applicable. What we will discuss in the upcoming videos. So today's concept regarding the binding energy, simply I can say that when nucleons are coming together to form the nucleus, they lose some energy to hold together in a nucleus. That is the binding energy. Another way I can say that the amount of energy required to break a nucleus into its constituents is called the binding energy. Otherwise, we can say that when the nucleons come together to form a nucleus, they lose some energy, which is the binding energy. So, before closing, I would like to give a mathematical example. It will be more clear. Suppose I am taking mass of a hydrogen atom. See here. This is the example. Mass of atom. It is 1.007825 unified mass. Similarly, I am writing mass of a neutron is equal to 1.008665 unified mass, and again I can write that mass of alpha particle or helium atom, you can write helium atom is equal to 4.00260 unified mass. I have written mass of a hydrogen atom, mass of a neutron and mass of helium atom. So when they make one alpha particle, how much energy they lose? You know that an alpha particle consists of two protons and two neutrons. Alpha particle consists of two protons and two neutrons. Okay, so if I calculate the binding energy, B, this is equal to how many protons? Two protons and two neutrons. So I can say 2 into 1.00785 unified mass plus mass of two neutrons, that is 2 into 1.008665 unified mass minus mass of the nucleus, that means mass of the alpha particle, which is given 4.00260 unified mass. This is for the mass purposes I have written C square. Okay, so in this case I can use here one unified mass, that is equal to 931 million electron volt per coulomb square. So if I calculate this, it will come around 0.03038. Okay, so C square. So in this case I can convert into energy by multiplying 931, that means 0.03038 into 931 million electron volt. So if we calculate, it will be almost 28.3 million electron volt. This is the binding energy of the helium nucleus. That means when two protons and two neutrons combine together, the amount of energy lost is equal to 28.3 million electron volt. Here what I have done, I have taken the mass of protons plus mass of neutrons minus mass of the helium nucleus. Together I multiplied with the C square, that is the formula for energy equal to mc square. Actually this difference between the sum of the masses of the nucleons and mass of the nucleus is the mass defect we have studied. Okay, that mass defect, the loss in mass only converted into energy, which is called the binding energy. I hope that you might have understood this topic. I expect that you will watch this channel sincerely. If you are not subscribed, you have to subscribe. Until the next video, bye.